Welcome to the fourth episode in a series where I make a solar power control system for my house. Now this episode should be the last one describing this first controller that I made, and hopefully that means we'll be getting back to more regular programming, whatever that might mean. Even so, this solar controller work has provided some great source material, so you'll likely see some related stuff making an appearance in my PCB making and programming series, so look forward to that. In this episode, I will show you how I implemented the control system for the inverter and the automatic changeover unit. But before describing the way I built this, let me quickly review how we got here just to make sure that everyone is up to speed. So originally, I did not immediately plan to make a controller for this solar system, and instead I was just intending to use simple off-the-shelf components. That included an automatic changeover unit, or ACO, that would simply switch between the solar and grid as the battery charged and discharged. Unfortunately, I found that as the inverter would still be idling even when the power was switched to the grid, this idling was just enough to cause the battery to over-discharge, causing the battery to go offline, rendering the system totally inoperable. So the primary goal of this whole controller project was to completely remove the inverter's load from the battery whenever it wasn't in use. But I also needed to find a way to make sure that the operation of the ACO and me powering the inverter on and off are synchronized in such a way that the power is not momentarily lost at the point of switching. Fine-tuning the switch on and off voltages of both the ACO and the inverter controller likely could be a way to solve this, but it's going to be pretty tricky to set up and manage these independent control systems. And if I was going to go to the effort of making a controller for the inverter, then controlling the ACO with that same system is an obvious choice. So that's what I did. Actually, the ACO was the easiest thing to control, so let's take a quick look at that first. Normally, the ACO is powered by the battery bus, and this same power source is what the ACO uses to sense when it needs to switch between the solar or the grid power. In the case of switching to grid power, this will happen when either the battery voltage is too low, but it also happens when the battery voltage is not present at all. And to force the ACO to switch to the solar power, first we need to pre-configure the ACO to switch on at the lowest possible voltage, and then by simply reconnecting the battery input, we can be sure that the ACO will switch to using the solar power. Of course, as a safety net, the ACO still needs to have a somewhat sensible configuration, making sure it will always switch to the grid if the battery volts get critically low. Now I found the battery input going to the ACO is actually completely isolated, so that allows for the option of either switching on the positive or negative leg of the supply. And as I have an abundance of N-channel MOSFETs kicking around, and also because it's an easier circuit to do, I decided to go with a low-side MOSFET style control. I also added a self-resetting fuse for some basic protection and an LED on the controller board so I can see when the ACO is being powered on. Actually, with the way that I've implemented this design, I probably could have just used a relay instead of this expensive ACO. But as I had already bought the ACO and installed it, it just made more sense for me to keep using it as it is. Alright, now let's move on to the inverter control. The power input of the inverter is rated at about 100 amps or so trying to actively switch that was simply not a good option. The inverter, however, has a little power switch on the front panel, and clearly it is not switching 100 amps, and it's fair to assume that this would be some sort of signal or low current switching. In any case, an obvious candidate for hacking by installing a remote controller relay or something like that. But this particular inverter I bought also came with a nice little remote control panel along with a cable. It provides for some basic status information, including DC bus volts, and notably, it has a power switch for remotely switching the inverter on and off. I'm guessing these inverters with remote control panels must be pretty popular for vehicles such as camping cars and boats and stuff. Anyway, let's take a look at how this one works. In trying to reverse engineer this panel, I'd actually prepared myself for a bit of a struggle, expecting to need to decode some tricky communications protocol or something like that. But thankfully, it was about as simple as it could get. Looking at the connector, coming into the board is the battery bus volts, which is always present. But there's also a 12 volt power supply rail, which is only present when the inverter is powered up. This 12 volt power supply then goes through a 7805 voltage regulator to create a 5 volt power rail. This powers the microcontroller and related stuff, I guess. The microcontroller itself is a Taiwanese Nuvoton, I don't know that brand, but anyway, a Nuvoton N76E003AT20. Seems like it's nothing special, just your basic 8-bit microcontroller with a bunch of IOs, ADCs, stuff like that. What was surprising, however, about the way they're using this is that there are no data connections from the connector to the microcontroller. In fact, the only apparent input to the microcontroller is the battery bus voltage, which is first conditioned with a voltage divider and some filter caps. And actually, that's all this microcontroller does. It simply measures the battery voltage using its internal ADC and then displays it both on this little bar graph and the 3-digit 7-segment display. And if I followed all of these little traces back to the microcontroller, I think I'd be able to confirm it, but I'm pretty damn sure they're using time division multiplexing to light up all of the different segments of these displays because, well, there's not enough IOs on the microcontroller to be able to serve all those individual segments. Below the voltage display, we have these two standalone LEDs here. One is for the power indicator and the other one for a fault indicator. Actually, these are not connected to the microcontroller and have nothing to do with it whatsoever. Instead, the power LED is driven by that 12 volt rail from the connector. The positive side of the fault LED is also powered by the same 12-volt rail, but the negative side goes to the connector to be driven by a signal directly from the inverter. And finally, the power switch on the panel just connects between battery voltage and returns the switch signal on a dedicated pin on the connector. The switch itself is simply a latching push button toggling between open or connected to battery voltage, and when this switch is closed, that causes the inverter to turn on. I'm guessing that this switch is probably just connected in parallel with the front panel on the inverter itself. I think that's pretty likely. So what have we got to work with here? Well, we can completely ignore the microcontroller stuff. The power LED and fault LED, however, would be useful to detect the general health of the state of the inverter, I think, and it's easy enough to safely interface to these signals. All we need to do is put optocouplers in place of where those LEDs would normally be. And finally, we have the inverter switch control, being the original goal of this endeavor. As inverters are incredibly noisy, we're going to need isolation when connecting to the ESP32, be it using an opto isolator or relay, and generally I would prefer to use a solid state solution for this connection, but as I don't know enough about the inverter's internal circuits, I judge it to be pretty risky in this case. So I decided to go with a relay-based solution, a latch relay to be specific, and for those who don't know what that is, a latch relay typically has 2 coils instead of 1, and you only need to momentarily energize either coil to switch between one state or the other. And after the state has changed, you no longer need to power the coils to maintain the state. I guess you can sort of think of it as a single bit non-volatile memory, but made from a relay. Now there's a couple of reasons why I actually chose a latch relay in this case. As latch relays coils don't need to be constantly energized, this of course is going to reduce power consumption, and it should also improve the long-term reliability of the relay itself. I was also worried about the case where the ESP32 might suffer an upset and interrupt the static signal controlling a normal relay, and that in turn might result in some sort of power disruption. Of course, using a latch relay can't guarantee that an ESP32 upset wouldn't cause a power disruption, but the hope is that it would improve the odds that it won't. So here you can see how I've wired up the relay with NPN resistors to drive each of the coils. And as this relay conveniently had 2 sets of contacts, I decided to connect up the second set of contacts to return the current state of the relay back to the ESP32. And I also added a LED indicator to the same set of contacts to make it easier to identify the state of the relay. And with regards to how I connected everything up, well, that's pretty much everything. Well, it's probably worth mentioning that the RJ45 remote cable supplied with the inverter is not actually a standard LAN cable with twisted pairs, and seems to be connected straight through. So instead of trying to make my own custom cable, I decided it was safer just to keep using that cable, and so I desoldered the connector from the original remote control panel and made a little adapter cable that could easily connect into my board. So let's move on. Now I'm not going to go over all the coding and detailed logic of the control system in detail in this video, but here at least is a consolidated view of everything we have to work with, and for the rest I'll leave up to your imagination. The control side of things is pretty simple as we discussed. We can control both the ACO and the inverter, and having control of both of these is great, because we can now create a startup sequence that ensures power isn't disrupted, but that also allows us to shut down the inverter quickly when it's not being used. As for the process of making the decision to switch between solar and the grid, and vice versa, there are really 2 objectives that I had in mind. The first is, I wanted to make use of every watt of solar power that is generated, well, for obvious reasons. And second is, I wanted to try to minimize the frequency of switching between the solar and the grid power. This is in order to minimize the wear and tear on both the batteries and the switching hardware, making the system hopefully cheaper to operate and more reliable too. So clearly, making a good judgment on when to switch is going to be important in achieving these goals, and having a mix of current, historic and forecasted information are things that can really help us make the best possible decision. And as I have a bit of a habit of overthinking things, I did have a couple of gems in mind, such as follows, like getting real-time weather forecast information from the internet, or placing some type of weather station and a light sensor on my roof, or even making use of the projected day-by-day sunrise and sunset times. Unfortunately, these 3 ideas are ones that didn't make it into the current build, but it might make it in there in the future. So here's what I actually used. The first is the solar battery voltage, and I use that to detect when the battery is actually being discharged, and it also helps to understand the general state of charge. And then I have the solar battery accumulated charge during that waiting period, obviously. Ultimately, this is historical information that allows a more accurate picture of what the battery's state of charge is. And then I have the current time of day, which I can use to determine what, if any, charge might be possible for the remaining part of the day. In addition to these items, which really focus on the state of charge, we also have some general system health information, such as system temperature, the state of the control relay that is switching on the inverter, the presence of that internal power rail from the inverter, and the information coming from the inverter regarding its fault state. This health information is used to stop the system from trying to activate when obviously it's in a very poor health state. It also helps in the case where the system is being activated and later on a poor health state is detected, and then the system can quickly shut itself down, switching back to using power from the grid. And I gotta say that interface that I built to get the status information directly from the inverter itself turned out to be really useful. Without that information, I would just be blindly switching the ACO to solar power, regardless if the inverter was even operating correctly or not. Alright, time for a demonstration. Now I actually recorded this video just before I installed the system under the floor, and please bear with it if you can, because it's not really the best recording I've ever done. It seems like I was getting pretty sick of the project by the time I recorded this, and I managed to repeat myself with a short demo of the CPU battery backup system again. But in this case it's sort of shown in combination with the inverter operation sequence, so I left it in, skip it as you see fit. In any case, I think the video covers most of the system well enough, and it sort of ties everything together, so let's check it out. So in this initialized state, that means the first time the system's been booted, it doesn't know how much capacity is being charged into the battery, so it doesn't really know if it's a good situation to actually execute or operate the inverter or not. So it has a pretty high set voltage, I think it's around about 25.9 volts. So once it sees the voltage get above 25.9, it will run. The other thing is that it's pretty critical on time. It has to be early in the day, so between 6 AM and 3 PM in that sort of time frame. If it gets up to that 25.9 volts, well then it will allow the system to run. Otherwise it will hold over to the next day and wait for that charge to reach that voltage. So let's increase the voltage and see the system kick in. So at 25.7, 9, you can see the voltage here. And actually let's go into the inverter control page as well and have a look. Maybe I should just point out what these various things are before we actually do it. So there are 4 status here which are being shown, and it shows that if the automatic changeover or the mains changeover box has been enabled or disabled, the inverter is set, it's currently stable. So if the inverter is being told to be switch on or switch off, and then there are 2 return or sense feeds that come back, which is the power state, so that if it is being sensed that the inverter is actually switched on, and if there's a false state on the inverter. So when this system starts up, normally what we're going to do is we're going to switch the inverter on, and then we're going to see that the power state of the inverter will come on, and then after a little while the inverter fault state clears. So initially when the inverter starts up, it sends out a fault state, which sort of makes sense, and once it has a stable voltage on the output, it clears the fault state. So once the fault state and all of this is clear, it waits a little while, and then it will actually turn on the mains changeover switch so that the power can be supplied. Alright, let's run it up, and I'll keep increasing this voltage now. Oh, and I should mention here, these 2 LEDs. This LED here is indicating that the inverter has been told to switch on, and this LED here is indicating that the automatic changeover has been told to turn on. So this yellow LED is the same as the inverter is set. The white LED is for the changeover, okay? Alright, let's increase that voltage, 26.9. We should start seeing some action. So it's turned on, and the inverter is on, the fault is cleared, and now we're in a stabilization period where I'm actually waiting and watching the temperatures and the voltage to make sure it doesn't drop too low, and then we are switched on. So now the inverter is on, everything's working nice, and if I start dropping the voltage on the power supply, it will look, I think it's 22.8 volts, it will then switch off the inverter. So you've seen there the automatic changeover switched off pretty quick for about 1 second before the inverter actually turns off, and then it turns off the inverter, and now we're in the waiting state. So while we're at this 22.78 volts, you'll see that we are still using the external power supply, and you might see this battery continue to drop over time, because this is actually creating some load on the system, and also the solar control itself creates some load on the system, and if it's at night time, there's going to be a draw on the battery. So this voltage will continue to drop overnight, and I think my hope is that it will sort of stabilize or recover some voltage before it drops too low. But the idea is that there's really inclement weather and this voltage continues to drop. We want to remove the load here, so 22.4 volts, and you can see now it's switched to internal battery to drive this system. So now the loads on the main bus is very, very low, just the solar controller itself. So as we recover, we will see the backup battery system recover. The battery backup system is no longer being used. We keep going, 25.9 or 26.9 did I say? So back up to 27 volts, but you'll notice the system does not start up. So the initialization state and the waiting state are different. They're not the same things. In the waiting state, we know that we've had a full discharge cycle, so to be able to switch back on, it can now make a judgment on whether to switch on back on based upon how charged the battery, or how much charge the battery has received. So the conditions for switching on from the waiting cycle is that it must have 1.2 kilowatt hours worth of charge going into the battery. But on the other hand, the time restrictions and the voltage restrictions are less. I think I switch on around about 25.6 or a much lower voltage than from the initialization states. In addition to the voltage being a little bit looser, the time is looser as well, so it will allow you to switch on if it sees enough charge going to the system by around about 5 p.m. The logic just switches just a little bit, but the key difference is that once we've gone through that charging cycle, we'll know how much charge is going to the battery, and we make a good judgment based upon the time of day if we want to switch the inverter on and start discharging that battery. There are a few manual controls here, and they all, once again, operate based upon the scenario. We can manually run the system up. And we can also manually stop it. And here we have an offline button. So the offline mode here that we have just means that it will no longer try to activate the inverter automatically based upon any conditions. It's just sitting there in an idle state. Obviously the system's going to charge because there's nothing stopping it from charging. So if you have some sort of weird problem with your inverter and you know it's not working or something else, you can just stop the automation from trying to switch on whatsoever. Press it again and we get back into that initialized state. If there are any errors that occur, the system will get into a fault state. Let's just run it. You'll notice that the run button is not working because there's a lockout on the run button so that you can't hammer it, so it's about a 1 minute lockout. So let's run it. And I'll cause an error by just turning off the power supply to the inverter directly with the isolation switch. So the internal inverter power is not found and we've failed. In this mode it's not going to automatically run obviously or recover itself. You need to clear the error and then it will back in that initialize stage. Yeah, so that's it for the demo. A bit rough, but hopefully you got the idea. Of course, if something was unclear, don't be afraid to ask a question in the comments. So, as I said at the start of the video, this is pretty much it for the core of this series. If something interesting related to this current system happens, then I might post a community message or maybe even a quick video. We'll see how it goes. Ultimately, I do plan to completely rebuild this controller, likely using a DIY PCB as well as an improved current sensing system, but I expect that's going to be some time off from now. But as it is, the system has been working really well. I think I made some small settings changes once or twice, but that's about it. Otherwise, the system has really been working perfectly. Actually, I've been really happy and honestly a little bit surprised it's working so well, especially how stably the ESP32 has been performing. During the development process, I did actually find the ESP32 to be really flaky and quite unstable. I was always having to reboot it to recover it, so I sort of prepared myself for the worst sort of case. But clearly, the stability issues must have been problems with my early coding design, and considering the fact that it's been really stable now, it's not only a sign that the ESP32 can be stable under the type of loads that I'm trying to place on it, but it also seems to show that I now have enough of a handle on programming the ESP32 to be able to write something that can be somewhat stable. Likely talk more about that in my programming series at some point. Anyway, enough rambling for now. Probably going to take a bit of a summer break, so can't be sure when my next video will be or what it might be about. But whatever it is, or whenever that might be, I do hope you join along. So, I'll see you then.